There is something buried in the rock, not a fossil, not a bone, not the outline of a creature pressed into stone by the slow weight of time. What is buried there is something quieter than that, something you would walk right past if you didn't know what you were looking for. It is a thin layer in the sediment, almost invisible to the untrained eye, stretched across the bottom of ancient ocean floors and the walls of exposed cliffs all around the world. And written inside that layer, in the language of chemistry, in ratios of isotopes and concentrations of carbon, is a story that scientists have been trying to decipher for decades. A story about something that happened 56 million years ago. You don't need to sit up for this. You don't need to take notes or hold on to anything tightly. Just let your body settle into wherever you are right now. Let your breathing slow down a little, and allow your mind to drift gently into what we're about to explore together. Because this is the kind of story that asks nothing from you except your quiet attention. The kind of story that has a way of expanding the space inside your thoughts, stretching time out in all directions until the present moment feels small and soft and strangely peaceful. 56 million years ago. Take a moment and just hold that number loosely in your mind, not as something to calculate or compare, just as a feeling, a sense of distance, a long, slow corridor of time leading backward into a world you would not recognize. The continents were in different places. The oceans were warmer. There were no ice caps at the poles. Forests grew in places that are frozen tundra today. And in that ancient warmer world, something happened. Something that geologists still argue about. Something that left a mark so deep and so strange that it has never been fully explained. Thousands of gigatons of carbon entered the atmosphere in what amounts, on geological timescales, to the blink of an eye. A few thousand years. Maybe 10,000. Maybe as few as 5. In a world where events are normally measured in millions of years, this was instantaneous. The climate lurched. Global temperatures climbed by 5 to 8 degrees Celsius, roughly 9 to 14 degrees Fahrenheit. The oceans became more acidic. Entire groups of deep-sea creatures went extinct. Ecosystems that had been stable for millions of years were reorganized from the bottom up. And then, slowly, over the following 200,000 years, the carbon was absorbed, the temperatures dropped, and the world settled into a new kind of normal. That event is called the Paleocene-Eocene Thermal Maximum. Scientists shorten it to the PETM, and it is one of the most carefully studied, most widely referenced, and least fully understood events in all of Earth's geological history. Before we go any further into the deep past, if you're the kind of person who finds comfort in the vastness of geological time, who loves falling asleep to questions that are too large for any single answer, then this channel is exactly the kind of place you might want to stay. Take a moment, if you feel like it, to hit the subscribe button and leave a like on this video. It genuinely helps this channel reach more people who are lying in the dark right now, just like you, looking for something slow and interesting to carry them towards sleep. And now that we've said that, we can let that thought go and keep moving. In 2018, 2 scientists published a paper that almost nobody read. Not because it wasn't important, not because the science was poor, but because the question it asked was so strange, so disorienting that most readers didn't quite know what to do with it. The scientists were Gavin Schmidt, who at the time was the director of NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester. Together, they wrote a paper asking a question that sounds at first like the premise of a science fiction novel. Could an industrial civilization have existed on Earth before humans? And could we have lost all trace of it in the geological record? They called it the Silurian hypothesis. The name comes from an episode of a science fiction television program, one that imagined a reptilian species that evolved intelligence long before humans arrived. But Schmidt and Frank were not writing science fiction. Their paper was published in a peer-reviewed scientific journal. They were asking a methodological question. A question about the limits of what we can actually know about deep time. Here is the thought experiment they started with. Imagine that every human being vanished from Earth tomorrow. Every city, Every road, every factory, every power plant, every wire and pipe and tower and dam, all of it gone. The people who built those things, gone too. And then imagine coming back to Earth 10 million years later, as a geologist, and trying to figure out that we were ever here. What would you find? This is the kind of question that seems simple until you really sit with it. And the answer, when you follow it all the way down, is deeply strange. Start with the obvious things. The buildings. Steel and glass and concrete. We tend to think of these as permanent, the way cities feel permanent when you're standing in one. But on geological timescales, concrete has the staying power of a sandcastle at low tide. Within 10,000 years, most structures would be unrecognizable. Within 100,000, the landscape would look almost natural again. Rivers would have shifted course. Forests would have reclaimed the streets. Erosion would have smoothed away the edges of everything we built. Within a million years, the surface of the planet would look, to most eyes, as though nothing unusual had ever happened there. And we're only talking about a million years. Schmidt and Frank were thinking about 10 million, 50 million, the kind of time where even the rock itself gets recycled, where ocean floors get pulled down into the mantle, melted and reborn as new crust, where mountains rise and then wear away to plains, where the oldest rocks on the surface are not windows into the distant past, but survivors of extraordinary geological luck. The oldest ocean floor on Earth is only about 200 million years old. Everything that came before it was subducted, dragged down into the heat of the planet's interior, and destroyed. The continents are older, but their surfaces are in a constant state of erosion and reworking. Very little survives intact from more than a few 100 million years ago, and what does survive is almost never the surface where life was actually happening. So, if we disappeared today, the physical record of our civilization would be gone within a few million years. Not degraded or obscured. Gone. Recycled back into the planet that made us. And this is where the question that Schmidt and Frank were really asking begins to come into focus. If physical structures don't survive, if cities and roads and buildings dissolve back into sediment long before any future geologist comes looking, then what would actually remain? What traces would an industrial civilization leave that could persist for tens of millions of years? The answer they arrived at after careful analysis is both elegant and unsettling. Chemical signatures. Not things, not shapes, not the outline of a building or the shape of a tool. Just chemistry, ratios of elements, concentrations of certain molecules, changes in the isotopic composition of ancient rock layers that would look, to someone analyzing a sediment core millions of years from now, slightly unusual, slightly off from what a purely natural geological record would show. Specifically, they identified a handful of markers that might survive long enough to be detected: a spike in certain synthetic molecules, an unusual concentration of plastics, slowly broken down into simpler organic compounds but potentially leaving a faint chemical trace, a thin layer enriched in radioactive isotopes from nuclear testing, a shift in the ratio of carbon isotopes in sediment layers, the kind of shift you'd see if enormous amounts of organic material were burned in a very short period of time. That last one, the carbon isotope shift. That is the one that matters most for what we're going to explore tonight. Because here's the thing. When Schmidt and Frank looked at that list of chemical markers that would indicate an industrial civilization had existed and then disappeared, they realized that one of them had already been found. Not as a prediction, not as a hypothetical. Already found, already studied, already documented in hundreds of sediment cores from every ocean and every continent on Earth. The carbon isotope excursion from 56 million years ago, the chemical fingerprint of the PETM, and the fingerprint matches. Not approximately, not loosely. When you look at the isotope data from PETM rock layers, the shift in carbon-12 to carbon-13 ratios is exactly what you would expect to see if someone had burned an enormous amount of organic material, fossil fuels, ancient carbon, The same signature we are creating right now with our factories and our cars and our power plants. The rocks from 56 million years ago look chemically identical to what industrial civilization looks like. Let that sit for a moment. You don't have to do anything with it. Just let it be there, like a stone dropped into still water, the ripples moving slowly outward in the quiet. Now, to be careful here, because precision matters when we're talking about something this important. Schmidt and Frank are not saying there was a civilization before us. They are not saying the PETM was caused by ancient industry. What they are saying is something more careful and more philosophically interesting than that. They are saying that if such a civilization existed, we might not be able to tell, that the geological record has a blind spot, that the same chemical signatures we associate with industrial activity are also producible by certain natural processes, and that without additional evidence, the chemistry alone cannot tell the difference. This is a statement about the limits of knowledge, about what the rock can and cannot tell us, about the gap between what happened in the deep past and what we can actually reconstruct from the evidence that survived. And that gap is wider than most people realize. Carbon, as you may already know in a general way, comes in different forms. These forms are called isotopes, and the difference between them comes down to how many neutrons are packed into the nucleus of each atom. Carbon-12 has 6 neutrons. Carbon-13 has 7. Both are stable, meaning they don't decay over time. Both exist in the atmosphere and in living things and in rocks all over the world. The ratio between them is not random. It is shaped by processes. When plants absorb carbon dioxide during photosynthesis, they preferentially take in carbon-12 because it is slightly lighter and slightly easier for biological chemistry to work with. This means that organic material, anything that was once alive, tends to be enriched in carbon-12 relative to carbon-13. When you burn organic material, that carbon-12 enriched carbon enters the atmosphere. And when that carbon gets absorbed into ocean sediments or locked into rock layers, the shift in the isotope ratio is preserved. Geologists can read it millions of years later like a timestamp, like a record of what was happening in the carbon cycle at a specific moment in time. The PETM shows one of the largest and sharpest carbon isotope excursions in the entire geological record. The ratio shifts dramatically toward carbon-12. It happens over just a few centimeters of sediment in fast-depositing ocean cores, which represents decades or centuries at most. It is, by any measure, a sudden and enormous injection of carbon-12 enriched carbon into the global system, and no one has fully explained where it came from. That is the mystery at the center of tonight's story. Not an ancient civilization, not a lost technology, not anything fantastical or extraordinary. Just a question that has been sitting in the geological record for decades, waiting for an answer that hasn't fully arrived yet. Where did all that carbon come from? The conventional explanations involve methane, specifically a type of methane stored in the deep ocean in ice-like structures called methane clathrates. Imagine, if you will, a kind of crystalline cage made of water molecules arranged in a lattice, with a methane molecule trapped inside like a fly in amber. These structures form under high pressure and low temperature, exactly the conditions that exist in deep ocean sediments. And there are billions and billions of tons of methane stored this way, quietly in the mud of the ocean floor. The theory goes like this. Something warmed the ocean. Slightly at first, maybe volcanic activity, maybe a shift in ocean circulation, maybe something else entirely. But as the water warmed, the methane clathrates in the upper layers of the sediment began to destabilize. The cages broke open, the methane was released, and methane is a potent greenhouse gas, many times more powerful than carbon dioxide over short time periods. So the methane entered the atmosphere, warmed the planet further, which destabilized. More clathrates, which released more methane, which warmed things further. A feedback loop, a runaway process. The kind of thing that once started is very difficult to stop. This explanation is plausible. It fits certain aspects of the data. But it has problems. The volume of methane required is enormous. You would need to destabilize a significant fraction of all the methane clathrates in all the world's oceans simultaneously across many different depths and pressures and temperatures. The trigger would have to be global in scope and sudden in effect. The timing doesn't quite work either. Methane clathrate destabilization should be gradual, ramping up over tens of thousands of years as warming slowly penetrates deeper and deeper into the ocean sediments. But the PATM carbon spike is sharp. It rises fast, much faster than a gradual release would produce. And then there is the isotope signature itself. Methane from clathrates is extremely depleted in carbon-13, more depleted than organic carbon from most sources. If the PETM was caused purely by methane release, the isotope excursion should be more extreme than what we actually see. It should lean further toward carbon-12 than it does. Instead, the signature looks like something in between, like a mix, like a blend of different carbon sources, like in fact the signature you would get if you burned very large amounts of ancient organic carbon, coal and oil and natural gas, fossil fuels. The carbon in those materials is organic in origin, enriched in carbon-12, but not as extremely as pure methane. The isotopic signature of the PETM falls right in the range you would expect from large-scale combustion of fossil fuels. Of course, 56 million years ago, there were no humans. There were no machines, no engines, no industrial civilization. Whatever burned the carbon, if anything burned it, was not a technological species. Or was it? That is the question Schmidt and Frank were brave enough to put into print. Not because they believe the answer is yes, but because they wanted to know whether the question was even answerable, whether our tools for studying the deep past are precise enough to rule out something as unlikely as an ancient industrial civilization. And the answer, they found, is that we cannot rule it out. Not with certainty, not based on chemistry alone. The fossil record offers some resistance to the idea. We have fossils from before, during, and after the PETM. We can see the evolutionary lineages of animals passing through the event. We see extinctions, yes, and radiations of new species. But we see biology responding to environmental stress. We do not see the hallmarks of civilization, no evidence of agriculture, no signs of construction, no sudden appearance of domesticated species, no tools, no technology. But here is the quietly unsettling truth about the fossil record. It is fragmentary. It is riddled with gaps. Most organisms that ever lived left no trace at all. Fossilization requires a very specific and unlikely chain of events: rapid burial, low oxygen conditions, the right chemistry. And even then, most fossils are destroyed by geological processes long before anyone can find them. If you tried to reconstruct the biodiversity of the modern world based only on what is currently being fossilized, you would miss the vast majority of species alive right now. The fossil record for any given time period is a small, biased, incomplete sample of what was actually living then. The fossil record from 56 million years ago is fragmentary, good in places, useful, but not complete. Not nearly complete enough to say with total confidence that there was nothing there we have failed to find. And this is where we have to pause tonight, right here, in the middle of the uncertainty, right in that quiet space between what we know and what we cannot quite prove. Because the PATM is not finished telling its story. The carbon is preserved in the rock. The temperature shift is recorded in the isotopes of ancient shell fragments. The extinctions are written in the sudden absence of species that had existed for millions of years before. The mystery is real, and it is ongoing. And we, lying here in the dark all these millions of years later, are not as far from it as we might like to think. There is something about the way the rock preserves a moment, not the way a photograph preserves it, sharp and immediate, frozen in recognizable detail. The way rock preserves a moment is slower than that. More patient. It takes the chemistry of what was happening in the water, in the air, in the bodies of tiny organisms drifting through an ancient sea, and it locks that chemistry into mineral structure. It holds it there, under pressure, under heat, under the slow accumulation of everything that came after, for millions upon millions of years, until a scientist pulls a core sample from the ocean floor and holds that moment up to the light. This is how. We know what we know about the PETM, not because anyone was there, not because the event left any visible scar on the landscape that survived into the present, but because the chemistry was preserved, because the isotope ratios were locked into the shells of microscopic organisms called foraminifera, tiny creatures with beautiful, intricate shells made of calcium carbonate, smaller than a grain of sand, that lived in the ancient ocean and then sank to the bottom when they died and were buried, and became part of the sediment and waited. They waited 56 million years for someone to come looking. If you can imagine that, the patience of it, the sheer scale of that waiting, then you already have some sense of the kind of humility that studying deep time requires. These creatures did not know they were leaving a record. They were simply living the way all living things live, taking in what they needed, building their shells one layer at a time, drifting through a warm, ancient sea that no longer exists in any form you would recognize. And yet their chemistry survived. Their isotope ratios survived. The story they recorded in the mineral structure of their shells survived. And it is telling us something we are only beginning to understand. When geologists pull a sediment core from the ocean floor, they are pulling up a column of time. The sediment at the bottom is oldest. The sediment at the top is youngest. Moving up through the core is like moving forward through the pages of a book, except the pages are made of compressed mud and the words are written in chemistry. Different layers contain different species of foraminifera, different concentrations of organic carbon, different ratios of carbon-12 to carbon-13. And when you reach the layer that corresponds to 56 million years ago, something happens to all of those measurements at once. The species composition changes abruptly. Many of the deep-sea foraminifera that were abundant in the layers just below simply disappear. They are there in one layer and gone in the next, or nearly gone, their populations crashing to near zero in what amounts, in sediment terms, to almost no time at all. This is a mass extinction, recorded in the absence of shells, in the sudden silence of species that had existed for millions of years. The shells that do remain show signs of dissolution. Their surfaces are pitted, their edges are corroded. The ocean was becoming more acidic, and acid dissolves calcium carbonate. The shells were being eaten away even as they were being deposited, even before they could be properly buried and preserved. This tells you something about how severe the acidification was. It was happening fast enough to affect the preservation of the record itself. And then there is the carbon isotope ratio. In the layers below the PETM boundary, it is relatively stable. It varies a little the way any natural system varies, but it stays within a range that reflects a carbon cycle in approximate balance. Then, at the boundary, it drops sharply. The ratio shifts toward carbon-12 in a matter of centimeters. In a fast-depositing sediment, a centimeter might represent a few decades, a few centuries at most. The excursion is global. Scientists have found it in sediment cores from the Pacific, the Atlantic, the Indian Ocean, the Tethys Sea that no longer exists, in rock outcrops in Europe and North America and Africa, and the margins of what is now Antarctica. Everywhere the record is preserved. The same sharp shift appears at the same moment in time. The same message, written simultaneously in sediments on every ocean floor on Earth. Something changed the entire planet's carbon cycle in a very short period of time. Think about what that means for a moment. Not the mechanism, not the cause, just the scale. We are talking about an event that was truly global in its reach, not regional, not limited to one ocean basin or one hemisphere. The entire planetary system shifted at once. The atmosphere, the oceans, the chemistry of the deep sea, the temperature of the surface, the biology of entire ecosystems, all of it reorganized in what is by geological standards an eye blink. This is the central mystery of the PETM, not just where the carbon came from, but how the trigger, whatever it was, managed to affect the entire planet so quickly and so completely. Consider the alternatives that scientists have explored. We touched on methane clathrates in the first part of our journey tonight. The idea that deep ocean sediments, loaded with frozen methane, could have destabilized and released their cargo into the atmosphere. This remains the most widely cited mechanism. It has real explanatory power. Methane is a powerful greenhouse gas. A large enough release could absolutely trigger the kind of warming we see in the PETM record. But the volume required strains credibility. Estimates for the amount of carbon released during the PETM range from 3,000 to 7,000 gigatons. To put that in a frame of reference you might find useful, imagine every coal plant, every oil well, every natural gas facility on Earth running at full capacity for several centuries. That is roughly the scale of what happened during the PETM. And that scale needs to come from somewhere. From some reservoir of stored carbon large enough and accessible enough to be mobilized in just a few thousand years. The methane clathrate reservoir in the world's oceans is large, genuinely large, but mobilizing a significant fraction of it simultaneously across different ocean basins at different depths under different pressure and temperature conditions requires a trigger of extraordinary power and extraordinary geographic reach. Volcanism is the other candidate that comes up repeatedly. The PETM coincides in a general way with a period of intense volcanic activity in the North Atlantic. As the Atlantic Ocean was widening, rifting open along what would become the Mid-Atlantic Ridge, enormous volumes of lava were being erupted across what is now the seafloor between Greenland and Europe. This kind of large igneous province volcanism is known to be associated with climate disruptions. The Siberian Traps eruptions coincide with the largest mass extinction in Earth's history, 252 million years ago. The Deccan Traps in India coincide with the end of the dinosaurs, so there is a clear and well-established precedent for volcanism driving climate change. But the timing for the PETM is difficult. The North Atlantic volcanism was spread out over millions of years. The PETM carbon spike happened over thousands of years at most. You would need an unusually concentrated pulse of volcanic activity, all happening within a very narrow time window, to account for the speed of the carbon release. And there is another problem with the volcanic explanation. Volcanic carbon dioxide comes from the mantle, from the deep interior of the Earth, and it has a different isotopic signature than organic carbon. It is not as depleted in carbon-13 as the carbon we see released during the PETM. To match the isotope excursion, the volcanism would need to have somehow ignited or combusted large amounts of organic-rich sedimentary rock. Coal deposits, oil-bearing shales, ancient peat beds. The magma would have had to intrude through these organic-rich sediments and bake them, releasing their carbon into the atmosphere with the isotopic signature of burned biological material. This is possible. There is some geological evidence that the North Atlantic volcanism did intrude through sedimentary basins in certain areas. But again, the scale required is enormous, and the mechanism has to be fast. Everything about the PETM has to be fast. Whatever happened, it happened quickly. There is a third idea worth sitting with for a moment, the possibility of a comet impact. A large comet striking the Earth could deliver significant amounts of organic carbon. Comets are partly made of frozen organic material, hydrocarbons that formed in the cold outer regions of the solar system billions of years ago. An impact would vaporize that organic material and inject it into the atmosphere. It could also trigger secondary fires, dust clouds, and climate disruptions, but we have no physical evidence of an impact at the PETM. The asteroid impact that ended the dinosaurs 66 million years ago left unmistakable fingerprints, a global layer of iridium, a rare element that is abundant in asteroids but rare in Earth's crust, shocked quartz, mineral grains deformed by the enormous pressure of an impact, tiny glass spherules called tektites, formed from rock that was melted and thrown into the atmosphere by the blast. an impact crater now partly buried under the Gulf of Mexico. The PETM has none of these signatures. No iridium layer, no shocked quartz, no tektites, no crater. If a comet caused the PETM, it did so without leaving any of the physical evidence we would expect to find. That does not make it impossible, but it makes it very unlikely. And so we are left, as we keep being left, with explanations that are plausible in outline but incomplete in detail, with mechanisms that could, under the right conditions, produce something like the PETM, but that struggle to account for the exact speed, the exact magnitude, the exact isotopic signature of what the record actually shows. This is not a failure of science. It is an honest accounting of what the evidence tells us and where it goes quiet. Science is not a machine for producing certainty. It is a process of building models, testing them against evidence, and refining them when the evidence pushes back. The model for the PETM is a work in progress. It has been a work in progress for 30 years, and it may remain one for 30 more. What we know with confidence is this: the PETM happened. The carbon was released. The planet warmed. The oceans acidified. Species went extinct. And then, slowly, over the following 200,000 years, the carbon was gradually drawn back down. The climate stabilized. Life recovered. The recovery is its own kind of story, and it tells us something important about time. Carbon is removed from the atmosphere by several natural processes, but the dominant long-term mechanism is chemical weathering. When carbon dioxide dissolves in rainwater, it forms a weak acid called carbonic acid. This acid falls on rocks and slowly dissolves them, releasing mineral ions that wash into rivers and eventually into the ocean. In the ocean, organisms use those ions to build shells and skeletons. When those organisms die and sink, the carbon is buried in the sediment, locked away in rock, removed from the active carbon cycle for millions of years. This process is slow. It operates on timescales of hundreds of thousands of years. It cannot respond quickly to a sudden carbon pulse. It simply cannot work fast enough to absorb thousands of gigatons of carbon in a short period of time. So the carbon stays in the atmosphere, and the atmosphere stays warm, and the oceans stay acidic, and ecosystems stay disrupted for hundreds of thousands of years until the weathering process has quietly and patiently done its work. 200,000 years. That is how long the PETM recovery took. Lie still for a moment and let that number move through you. 200,000 years of elevated temperatures. 200,000 years of acidified oceans. 200,000 years of ecosystems struggling to reorganize themselves after the disruption. That is longer than modern humans have existed as a species. That is a span of time within which every human civilization that has ever existed could fit many times over and still not reach the end of the recovery period. And yet, on the scale of geological time, 200,000 years is not very long. It is a brief chapter, a footnote in a story that spans hundreds of millions of years. The planet absorbed the disruption and moved on. New species evolved to fill the niches left by those that went extinct. The climate found a new equilibrium. The carbon cycle rebalanced. Earth continued. But the species that went extinct did not come back. The ecosystems that collapsed did not simply restore themselves to their previous form. What emerged from the PETM was a different world. Not worse in any absolute sense, not from the perspective of the planet as a whole, but different, transformed, carrying the marks of what had happened to it. This is one of the things the PETM teaches us about planetary climate systems. They are resilient, in the sense that they do not simply stop functioning under stress, but they are not reversible in any simple way. When you push a complex system hard enough, it does not spring back to where it started. It finds a new stable state, and the path from the disrupted state to the new stable state is long and difficult and full of loss. Consider the deep sea foraminifera. 35 to 50% of deep sea forum species went extinct during the PETM. These were organisms that had survived for millions of years through earlier climate variations, through ice ages and warm periods, through the slow drift of continents and the gradual evolution of ocean chemistry. They had endured, and then, in the space of a few thousand years, roughly a third to half of them were gone. The ecological gaps they left took hundreds of thousands of years to refill as new species evolved to occupy the niches the extinct ones had left vacant. Evolution can work quickly under strong selection pressure, but it still works on the timescale of generations, of genetic variation accumulating and being tested against the environment. It cannot keep pace with the disruption that happens in centuries or millennia. It can only respond after the fact, picking up the pieces, building something new from what survived. On land, the story was different but no less dramatic in its own way. Mammals were the dominant large animals on land during the Patum, as they had been since the extinction of the non-avian dinosaurs 10 million years earlier. But the mammals of that time were not the animals we know today. They were smaller, generally, more generalized, occupying a world that was still being sorted out, still filling the ecological space left by the dinosaurs, still diversifying into new forms and new niches. During and after the PETM, this diversification accelerated. The warming created new environments, new ecological opportunities, new pressures that drove evolution in new directions. Early horses, which were small forest-dwelling browsers before the PETM, began evolving toward the larger, more open country forms that would eventually become the horses we know. Early primates, our distant relatives, underwent significant diversification during this period. In this sense, the PETM was not purely destructive. Disruption creates opportunity. When old ecological structures are broken down, new ones can form. Species that had been limited by competition with established forms suddenly found themselves with room to expand, to experiment, to evolve into forms that had not existed before. The PETM was, in a very real sense, one of the evolutionary events that set the stage for the world we live in now, including, at a great distance, for us. But there is something uncomfortable in that observation, something worth sitting with. The same disruption that created opportunities for some species destroyed others entirely. The balance between those two outcomes, the loss and the gain, is not easy to calculate. It depends on which side of the disruption you are on. For the mammals that could move, that could adapt, that had enough genetic flexibility to evolve new solutions to new problems, the PETM was a doorway. For the deep-sea foraminifera with their calcium carbonate shells dissolving in acidified water, it was a wall. We are now, as you may already know in the quiet way that these things settle into the mind, in the middle of our own thermal maximum. Not 56 million years from now, looking back at a thin layer in the rock. Right now, in the moment, watching it happen in real time, with instruments and satellites and sediment cores and atmospheric monitoring stations and decades of accumulated data. Global temperatures have already risen by about 1.1 degrees Celsius, roughly 2 degrees Fahrenheit, since the Industrial Revolution began. That does not sound like much. It is easy to hear that number and feel that it is small, but temperature is not the most intuitive way to understand what is happening. A better way is to think about energy. The Earth's climate system contains an enormous amount of thermal energy. The oceans alone hold more heat than the entire atmosphere. When you add even a small amount of heat to a system that large, the effects can be profound. A rise of 1 degree in average global temperature represents an extraordinary amount of additional energy distributed through the climate system. It shifts weather patterns. It changes precipitation. It moves the boundaries of ecosystems. It alters the timing of seasons. It accelerates ice melt. It changes ocean circulation. We are already seeing all of these things. Arctic sea ice is declining at a rate not seen in thousands of years. The Greenland ice sheet is losing mass faster than projections, made just a decade ago. Ocean circulation patterns are showing signs of weakening. Coral reefs are bleaching and dying at frequencies that were nearly unheard of 50 years ago. Extreme weather events, heat waves, floods, droughts, hurricanes, are becoming more frequent and more intense. And this is from 1 degree of warming. The PETM, which pushed temperatures up by 5 to 8 degrees, shows us what several more degrees would look like. Not as a prediction, exactly, because the PETM unfolded over thousands of years, while our current warming is happening over centuries, which makes it in some ways even more destabilizing. But as a reference point, as a geological case study in what elevated carbon dioxide does to a planet's climate system. The PETM also gives us a picture of what the oceans were like under that kind of chemical stress. During the event, ocean pH dropped sharply as carbon dioxide dissolved into seawater and formed carbonic acid. This acidification did not just affect the tiny foraminifera at the bottom of the sea. It affected the entire carbonate chemistry of the ocean, from the surface down to the deepest trenches. Today, ocean pH has already dropped by about 0.1 units since the Industrial Revolution. That sounds like a small number, but the pH scale is logarithmic, meaning a change of 0.1 units represents roughly a 26% increase in ocean acidity. Marine organisms that build calcium carbonate structures, corals, oysters, clams, sea urchins, pteropods, the tiny winged snails that form the base of many marine food webs, are already showing the effects. Their shells are thinner, their growth rates are slower, their survival rates in acidified water are lower. We are watching, in real time, the early stages of the process that drove those deep-sea foraminifera to extinction 56 million years ago. Have you ever watched something unfold slowly and known what it was, but been unable to stop it? There is a particular quality to that experience, a kind of suspended stillness, a sense of watching a film whose ending you already know, but hoping somehow that this time the story will go differently. That is something like what climate scientists describe when they talk about the PETM and its relationship to the present. They know the story. They have read it in the rock. They know how a rapid carbon injection plays out over geological time, and they are watching us write the same story again, in real time, at an even faster pace. We are releasing carbon roughly 100 times faster than the PETM did. The PETM released its carbon pulse over 5,000 to 20,000 years. We have released a comparable fraction of carbon in about 200 years, and we are accelerating. The natural systems that absorb carbon, the forests, the soils, the oceans, all of which are drawing down carbon dioxide and storing it in biomass and in deep water and in sediment, are working. They are absorbing roughly half of everything we emit, but they cannot keep up. The other half accumulates in the atmosphere year after year, and the concentration keeps rising. Before the Industrial Revolution, atmospheric carbon dioxide was about 280 parts per million. It had been at roughly that level for hundreds of thousands of years, cycling up and down with ice ages and warm periods, but staying within a familiar range. Today, it is above 420 parts per million. That is a 50% increase in less than 3 centuries. The last time carbon dioxide was at this level was approximately 3 million years ago, during the Pliocene, when global temperatures were 2 to 3 degrees warmer than today and sea levels were 15 to 25 meters higher. We are not in the Pliocene. We are at Pliocene carbon dioxide levels, but in a world that is still adjusting to the change. The planet has not yet fully caught up with the chemistry. The ice sheets that are out of equilibrium with current conditions are melting, but slowly. The deep ocean warming that will continue for centuries is only beginning to propagate downward. The ecosystem reorganizations that will unfold over decades and centuries are just getting started. There is a lag built into the climate system. What we feel today is the consequence of emissions from decades ago. What we emit today will shape the climate that our children and grandchildren inherit. And the carbon we emit in the next few decades will still be affecting the atmosphere thousands of years from now. The weathering process that removed the PETM carbon over 200,000 years is the same process that will eventually remove our carbon. Rain falling on rock, ions washing into rivers, shells forming and sinking. It will work. It always works. but it works slowly, and while it works, the heat remains. The oceans remain acidic, and the ecosystems remain disrupted. Think about what it means to commit a system to 200,000 years of elevated stress. Not intentionally, not as a choice made with full awareness of the consequences, but as the incidental result of burning the carbon-rich materials that drove an industrial civilization. Whatever caused the PETM, if it was a natural process, it did not choose to do what it did. It simply followed the physical and chemical laws that govern how matter and energy interact on a planet. We are the first cause of a planetary climate disruption that is chosen, that has seen the evidence, understood the mechanisms, and continued anyway. This is the strange and heavy thing about living in this particular moment in geological time. And yet, and this is worth holding on to as you drift toward sleep tonight, the planet has been here before. Not this exact configuration, not with these exact species and these exact ecosystems and these exact concentrations of carbon, but it has been pushed hard before, many times, and it has recovered, not to what it was before exactly, but to something livable, something capable of sustaining the further elaboration of life. The PETM ended. The carbon was absorbed, the temperatures came down, the oceans became less acidic, new species evolved, new ecosystems formed. Life, in its extraordinary resilience and creativity, found a way to inhabit the altered world and make something new of it. Earth is old in a way that our minds cannot fully compass. It has been through 5 major mass extinctions, each one far more severe than anything we are currently experiencing. It has been through periods of almost complete glaciation, when ice extended nearly to the equator. It has been through periods of intense volcanic activity that dwarfed anything in recorded human history. It has absorbed asteroid impacts, magnetic field reversals, the gradual brightening of the sun, the slow drift of continents, and through all of it, life has persisted. Changed, yes. Diminished in diversity at times, yes, but persistent. Stubborn, inventive, finding niches in the margins, surviving in refugia, evolving new strategies when old ones no longer worked. This is not a reason for complacency. The species that went extinct during the PETM did not experience the recovery as a consolation. They simply ended. And there are species alive today, many of them, that may end in the same way if the changes we are driving continue at their current pace. But it is a reason for a particular kind of perspective, the kind of perspective that comes from lying quietly in the dark and allowing your sense of scale to expand beyond the boundaries of a single human life, a single human civilization, a single century or millennium. The kind of perspective that sees the planet not just as the stage on which human history is played out, but as a participant in a much longer story that began billions of years before us and will continue billions of years after. We are part of that story. Not the whole of it, not the end of it. One chapter, extraordinary in its brevity and in the speed with which it is reshaping the conditions for all the chapters that come after. The PTM is that chapter from 56 million years ago. Dramatic, disruptive, still not fully understood, leaving the world changed in its wake, and yet not the end. What we do not know and cannot know is what chapter comes after ours. That depends on choices that are being made right now, in governments and boardrooms and laboratories and living rooms all over the world. Choices about energy and consumption, and land use and international cooperation. Choices about what kind of world we are willing to fight for and what kind of world we are willing to leave behind. But that is for the waking world to work out. For now, in the quiet of wherever you are, in the slow dimming of thought that comes with late hours and a long journey through deep time, there is something almost restful in the scale of it all. The planet has been through this before, not like this. Not at this speed, but the broad strokes are familiar. Carbon rises, temperature rises, oceans acidify, species struggle, And then, slowly, over time scales that dwarf human history, the system finds its balance again. New life fills the spaces left by the old. The chemistry stabilizes. The climate settles into something new. We are the first species that has been able to read the record of all of this and understand what it means. That is a strange and remarkable thing to be, to stand in the present, holding the geological past in one hand and the possible futures in the other, and to have to decide what to do with that knowledge. But that decision does not have to be made tonight. Tonight, the only thing required of you is to rest, to let the long, slow breath of geological time move through you, to feel how small and brief and precious this moment is, nested inside a planet that is itself nested inside a solar system, inside a galaxy, inside a universe that is still, after nearly 14 billion years, mostly a mystery. The foraminifera drifted through their warm ancient sea and left their chemistry in the sediment and did not know they were leaving a record. The carbon spiked and the temperatures rose and the oceans acidified, and then, eventually, everything settled. The rock remembered. And millions of years later, we came along and learned to read what the rock had kept. What we write in the rock now is still being decided. There is a kind of knowledge that lives in the body before it reaches the mind. The way you know, without looking at a clock, that it is very late. The way a familiar smell can return you instantly to a place you have not thought about in years. The way certain kinds of quiet have a texture to them, a depth that is different from the quiet of earlier in the day. You are in that kind of quiet now. The world outside has settled. Your breathing has slowed. And the story we have been moving through together, this long, slow journey into deep time and ancient chemistry and the mysteries written in rock, is beginning to close around you the way water closes around a stone. Let it. There is nothing you need to hold on to here. The ideas will still be there if you want them in the morning. The mystery of the pattern will still be there, unsolved, patient as stone. The questions that Schmidt and Frank put into their paper, the questions about what we can and cannot know about the deep past, will still be open, still waiting for new evidence, new interpretations, new ways of reading what the rock has preserved. None of that is going anywhere. For now, let the thoughts loosen. Let them drift. We have traveled a long way tonight. We started 56 million years ago, in a world unrecognizable to modern eyes, and we have moved forward through time, stopping along the way to examine the evidence, to turn the mystery over in our hands, to look at it from different angles. We have talked about carbon and isotopes and foraminifera and methane, clathrates and volcanic provinces, and the fragility of the fossil record. We have talked about what survives deep time and what does not, about the gap between what happened and what we can reconstruct from the chemical record it left behind. And underneath all of it, threading through every piece of the story like a quiet current, there has been one central question, not the technical question of what caused the pattern. That question is important, but it is a question for laboratories and field, seasons and conference papers and peer review. The deeper question, the one that has been humming beneath the surface of everything we have discussed tonight, is something more personal than that. What does it mean to know that a planet can be changed this quickly? Not in the abstract, not as a fact stored in a mental file labeled climate change, but as something felt, as something understood in the way you understand that winter is coming when the light shifts in September, or that a storm is building when the air takes on a certain weight, as something integrated into the body of what you know about the world you live in. The PETM is not a metaphor. It is not a cautionary tale constructed after the fact to make a point. It is a physical event recorded in real rock that happened on a real planet and left real consequences that unfolded over real time. The foraminifera that went extinct were not symbols. They were organisms with lives, with ecological roles, with relationships to every other part of the ocean system they inhabited. When they died, something real was lost. Not lost in the way a cultural memory is lost, fading gradually as the people who hold it pass away. Lost in the way that a species is lost, which is completely and permanently and without any possibility of recovery. Extinction is the most final thing there is. And yet, and this is the thing about the deep time perspective that is both troubling and strangely comforting, the ocean did not stop. The planet did not stop. Life did not stop. 200,000 years later, new foraminifera had evolved to fill the niches left by the ones that were gone. Not the same species, not replacements in any exact sense, but organisms capable of doing similar work in the ocean system, building calcium carbonate shells, processing carbon, contributing to the great cycling of materials that keeps the planet's chemistry in balance. Evolution does not mourn. It simply continues. This is one of the hardest things to hold in the mind at the same time. The reality of individual loss, the irreversibility of extinction, the weight of what disappears when a species ends, and also the larger continuity, the unbroken thread of life that has run through every catastrophe this planet has experienced and come out the other side changed but unbroken. Both things are true. The loss is real. The continuity is also real. And sitting with both of them at once, without resolving the tension between them into something more comfortable and less accurate, is one of the disciplines that deep time asks of us. The Silurian hypothesis, which we explored at the beginning of our journey tonight, asks a question that is ultimately about the limits of knowledge, about what we can and cannot see through the instruments we have built to study the past. Schmidt and Frank showed that an industrial civilization, if one had existed 56 million years ago, would leave behind very little physical evidence by the time we came looking. The structures would be gone. The artifacts would be dissolved and scattered. The technology would have left no recognizable trace. Only chemistry would remain. Only the subtle signature of altered isotope ratios, elevated carbon concentrations, the faint fingerprint of a civilization that burned its way through the world and then disappeared. And that fingerprint, as they pointed out, is exactly what we see in the PETM. Now, to be clear, as we have been clear throughout this journey, this does not mean there was a civilization. The scientific consensus is that the PETM was caused by natural processes. The fossil record, fragmentary as it is, shows no evidence of intelligent life during this period. The evolutionary lineages of animals pass through the PETM without any of the discontinuities or anomalies that the presence of a technological species might create. The conventional explanations, methane release, volcanic activity, orbital forcing, combinations of these, while incomplete, are far more consistent with the overall evidence than any hypothesis involving ancient industry. What the Silurian hypothesis demonstrates is not that the PETM was caused by a civilization. It demonstrates that we would not necessarily know if it had been, that our tools for reading the deep past have limits, that the absence of evidence is not always evidence of absence, particularly when the detection methods have known blind spots. This is a methodological insight, and it is a valuable one, not just for understanding the PTM, but for thinking about how we look for life elsewhere in the universe. If we are searching for signs of intelligent life on other planets, what are we actually capable of detecting? Radio signals, the traditional focus of the search for extraterrestrial intelligence, require an active broadcasting civilization. A civilization that has already destroyed itself would not be sending radio signals. It would be silent. All that might remain would be chemistry. A shift in the atmospheric composition of a distant planet. An unusual concentration of certain molecules. The kind of signal that might look, to an observer without context, like a natural geological or biological process. The universe may be full of these ghost signatures. Planets that once harbored technological civilizations, that burned through their resources, that pushed their climate systems past critical thresholds, and that then went quiet, leaving only a thin layer of disturbed chemistry in their geological records, leaving only the silence between stars. This is the darkest version of the Fermi paradox, the observation that the universe is vast and old and ought, on statistical grounds, to contain many civilizations if the conditions for intelligence are as widespread as we have reason to believe they are. And yet we see no evidence of any of them. No signals, no megastructures, no evidence of deliberate engineering at astronomical scales. One explanation is that civilizations are short-lived, that every species which develops the capacity for industrial civilization also develops, almost inevitably, the capacity to destabilize its own planet's climate, that the same cognitive abilities that allow a species to build engines and power grids and communication networks also allow it to extract and burn carbon at a pace that the planet's natural systems cannot absorb, and that this tends to end badly. This is what scientists sometimes call the Great Filter, the idea that somewhere between simple chemistry and galaxy-spanning civilization, there is a step so difficult, so dangerous, so prone to failure that almost no species makes it through. The question is whether that filter is behind us, in the improbable chain of events that led from simple molecules to complex cells to multicellular life to intelligence, or whether it is ahead of us, waiting at the point where a species first becomes capable of altering its own planet's climate and must decide whether to stop. The PETM offers a hint, though it is a hint and nothing more. It shows that planets can undergo rapid, catastrophic climate disruption. It shows that carbon release at industrial scales, whether caused by natural processes or by something else, has consequences that are severe and long-lasting and global in their reach. It shows that the climate system, which seems stable and reliable from the perspective of a human lifetime, is actually capable of lurching into dramatically different states under the right conditions. And it shows that whatever caused the PETM, whether it was methane or volcanism or something we have not yet thought of, the event ended relatively quickly in geological terms. The carbon spike is sharp in the record, it rises, and then it falls. Whatever the source of the carbon, it was exhausted. The system that was releasing it, natural or otherwise, burned through its reserves and stopped. This is worth sitting with, not as a cause for alarm, because alarm is not something that serves anyone well at this hour, in this kind of quiet, but as a piece of the picture. Whatever it was that drove the peep, it did not go on forever. It ended. The planet found its way back to balance. Not the same balance as before, but a balance, a new equilibrium, a world that was different in its specifics but recognizable in its basic structure as an Earth, with oceans and atmosphere and geology and life. That is what planets do, apparently. They absorb disruptions and continue. The question we are left with, the one that hums underneath everything we have explored tonight, is not really about the PETM at all. It is about us, about the species that evolved in the aftermath of the PETM, that descended from the mammals that survived its heat and its disruptions and its reorganization of ecosystems, that eventually developed the ability to read what happened in the sediment record and understand what it means, about whether we will be the civilization that looked at the evidence and changed course, or the civilization that looked at the evidence and continued anyway. This is not a question that needs to be answered tonight. It probably cannot be answered by any single person or any single decision. It is being answered, slowly and collectively, in the aggregate of 1 million choices being made simultaneously by billions of people and the institutions and systems they inhabit. Some of those choices are moving in the right direction. Renewable energy is growing faster than any previous energy transition in human history. The cost of solar power has fallen by more than 90% in the last decade. Electric vehicles are becoming more common. Forests are being protected and replanted. Carbon is being measured and in some places priced and in some places beginning to decline. None of this is enough yet. The trajectory still points toward warming that will dwarf what we have experienced so far. The carbon we have already emitted will continue to shape the climate for centuries. The ice sheets that are out of equilibrium with current conditions will continue to melt. The oceans will continue to absorb heat and become more acidic. The weather patterns will continue to shift and become more extreme. But enough is not a fixed point. It is a moving target, and every fraction of a degree of warming that is avoided is a real and consequential difference. Every year of delay in the peak of global emissions adds to the eventual total. Every year of faster action subtracts from it. The future is not a binary between catastrophe and safety. It is a spectrum of outcomes, and every choice matters. Every action shifts the probability distribution. Every degree avoided is a gift to every species that would otherwise have lost more than it could bear. The petty M took 200,000 years to resolve. We do not have 200,000 years. We have decades, perhaps less, the window for the most. Consequential decisions is narrow, and it is closing. But this, too, is not something that needs to be carried into sleep. Tonight, what you can carry is something quieter, something that does not require action or urgency or anything at all from you except the willingness to hold it gently, the way you hold a stone you picked up on a walk, not because it is valuable or useful, but because its weight and texture are interesting, and it connects you, in a small way, to something older than yourself. The PETM happened. The planet was disrupted. Life was lost and life continued. The chemistry was preserved in rock, and millions of years later we found it, and we read it, and we understood what it said. This is a remarkable thing, not because of what it tells us about the past, though it tells us a great deal, but because of what it says about us, about the kind of creature we are. We are the species that figured out how to read the past in layers of sediment. We are the species that learned to extract isotope ratios from the shells of microscopic organisms dead for 56 million years and use those ratios to reconstruct the temperature of an ancient ocean. We are the species that built the instrument sensitive enough to detect changes of a few hundredths of a unit in the pH of seawater, and understood what that change meant in terms of the organisms living in it, and connected that meaning to a chain of consequences that would unfold over decades and centuries. We are the species that can understand deep time. No other species on this planet has that ability. No other species can hold 1 billion years in its mind and trace the thread of continuity from the first self-replicating molecules to the cells, to the organisms, to the ecosystems, to the civilizations. No other species looks at a rock and reads a story. No other species sits awake at night or lies in the dark in the last moments before sleep and wonders about what happened 56 million years ago and what it means for tomorrow. This is what we are. Whatever else we are, however frightened or confused or uncertain, however capable of destruction and denial and short-sightedness, we are also this. Creatures capable of understanding the place we inhabit, capable of reading the record the planet has kept and grasping what it says. The foraminifera drifted through their warm, ancient sea and left their chemistry in the rock and did not know they were leaving a message. We have received that message. We understand. What we do with it, is still being decided, but not tonight. Tonight, you have traveled far enough, through sediment layers and isotope ratios and ancient methane, and the slow, patient work of chemical weathering, through extinct ocean creatures and evolving mammals and the long spiral of life reorganizing itself after disruption, through the thought experiment of what survives deep time and what dissolves, through the methodological caution of what we can and cannot know about the distant past, through the strange vertigo of realizing that the chemical signature we are creating right now, in the atmosphere of this living planet, may look to some future geologist exactly like the signature that has been puzzling scientists for 30 years in the rock record from 56 million years ago. You have traveled all of that, and now it is time to rest. Let the thoughts that are still moving slow down. Let them drift like sediment settling through still water, gentle and unhurried, finding their way to the bottom. Let the images from tonight, the ocean floor, the sediment cores, the warm, ancient sea full of tiny shell-building organisms, let them soften at the edges and become something more like a feeling than a picture. A feeling of depth, of time, of the extraordinary age and resilience of this planet you are resting on right now. The Earth beneath you has been here for 4.5 billion years. It has been struck by asteroids and drowned in lava, and frozen to its equator, and heated until the oceans steamed. It has watched 5 great extinctions come and go, each one taking with it the majority of the species alive at the time, and after each one, life has returned, different and new and stubborn, filling the emptied world with fresh elaborations of the same ancient biochemistry. You are one of those elaborations, a late and improbable and extraordinary one, made of the same carbon that has been cycling through this planet's crust and ocean and atmosphere for billions of years. The same carbon that was locked in ancient organisms and released by the PTM, and slowly drawn back down into the sediment. The same carbon that is in every cell of your body, that was once in a plant, that was once in the ocean, that was once in the atmosphere of a world that no longer exists in any form you would recognize. You are made of deep time. You are the universe turned toward itself, briefly, in wonder. And right now, the universe is tired, and it is time to sleep. Let your body become heavy. Let your thoughts become slow. Let the long, patient breathing of the planet underneath you carry you the rest of the way. There is nothing left to figure out tonight. The mystery will be there in the morning. The rock will still remember. The chemistry will still be there, preserved in the sediment, waiting for the next question. For now, there is only this: the quiet, the dark, the slow settling of everything into stillness. The PTM happened 56 million years ago, and the planet continued. You are here, right now, and that is enough. Let sleep come the way the carbon was absorbed, slowly, thoroughly, without urgency, the way rain falls on ancient rock and the rock receives it, and something is quietly, permanently changed. Good night.